Hi, welcome back to my channel. My name is Gina. In this video, we are going to look at an example of traveling mechanical waves, and we are going to find its displacement function. A wave is traveling on a string in the negative x direction with wave speed of 25 meters per second. The period of the wave is 30 milliseconds. At t equals to 0 seconds and at x equals to 0 centimeters, the transverse displacement is 2 centimeters and is traveling downward at 2 meters per second. What are the displacement and velocity functions? A quick recap. For a traveling wave that is traveling rightward, its displacement function is in the form of amplitude times sine of wave number times x minus angular frequency times time plus the phase constant. And for a wave that is traveling leftward, its displacement function is amplitude times sine of wave number times x plus angular frequency times time plus the phase constant. And the velocity function, which is the partial derivative of the displacement function with respect to time. So we are going to hold x as a constant, partial derivative of d with respect to time. So if we held x as constant, then inside the sine function we have some constant minus angular frequency times time plus another constant. And derivative of sine function is cosine function. And here we have an inner function, so we need to use the chain rule. Derivative of the inner function, if we held x as a constant, it is simply negative angular frequency. So negative angular frequency is derivative of the inner function, then times the constant in front, a, times derivative of sine function, which is cosine of wave number times x minus angular frequency times time plus the phase constant. And for the left traveling wave, the velocity function is similar. It's the partial derivative of the displacement function with respect to time. But here, the derivative of the inner function is angular frequency, so we don't have the negative sign. So angular frequency times amplitude times cosine of wave number times x plus angular frequency times time and plus the phase constant. In this problem, it's given that the wave is traveling in a negative x direction. So we are going to use the displacement function for left traveling waves, which is the later one. Let's call this equation 1 and the velocity function equation 2. So to find the displacement function, we need to find 4 constants. The amplitude, wave number, angular frequency, and the phase constant. Let's start with writing down the notes we have from the problem. It is given that the wave speed is 25 meters per second. And the period is 30 milliseconds. In standard unit, 0.03 seconds. The initial conditions are also given. At t equals to 0 and x equals to 0, we have the initial displacement is 2 centimeters or 0.02 meters. And the initial transverse velocity, Vy, at x equals to 0, it is downward at 2 meters per second, so negative 2 meters per second. How can we use this information to find the 4 constants? Let's start with the period. We know that angular frequency is 2 pi over the period. So angular frequency is 2 pi divided by 0.03, which equals to 209.4, and unit is radians per second. Then let's use the wave speed. We know that wave number is an analogy to angular frequency, but instead of in the time dimension, we are in the spatial dimension. So angular frequency is 2 pi divided by the time for one cycle, and wave number would be 2 pi divided by the distance for one cycle, which is the wavelength. And wavelength also equals to the wave speed times the time for one cycle, the period. So wave number is 2 pi divided by 25 meters per second, which is the wave speed, times the period, 0.03. And this equals to 8.38, unit is inverse meters. Now we have the angular frequency and the wave number. We still need the amplitude and the phase constant to write down the displacement function. And remember that amplitude and the phase constant are determined by the initial conditions. So now we need to use the initial conditions given. It's given that at x equals to 0 and t equals to 0, displacement is 0.02. And let's substitute x equals to 0 and t equals to 0 into our equation 1. Then we get amplitude times sine of phi naught. Similarly with initial velocity, it's given that initial velocity is -2, and we can substitute x equals to 0 and t equals to 0 into our equation 2. And we get angular frequency times amplitude times cosine of phi naught, the phase constant. Let's call this equation 3 and this equation 4. Here we have a system of equations. We have 2 unknowns and 2 equations. So we should be able to find amplitude and the phase constant. Let's do equation 3 divided by equation 4. The right-hand side of equation 3 and 4 are amplitude times sine of phi naught. And equation 4 is angular frequency times amplitude times cosine of phi naught. And this equals to 0.02 divided by -2, the initial conditions. We can cancel out the amplitude, and sine function divided by cosine function is a tangent function. So this also equals to 1 over angular frequency times tangent of phi naught. And it equals to 0.02 divided by -2, which is -0.01. And remember that we already found angular frequency, so we substitute the angular frequency in this equation. We get tangent of phi naught is about -2.094. Then we can solve for the phi naught. Phi naught would be inverse tangent of -2.094, and we get -1.12. But remember that tangent is a repeated function over pi. The sine and cosine, they are repeated over 2 pi. So another possible phi naught would be -1.12 plus pi, which is 2.02 radians. Let's call the first solution, solution A, and the second solution, solution B. The phi naught we want should satisfy the initial conditions. So let's check whether solution A or solution B satisfy the initial condition. Let's start with solution A. If we substitute phi naught equals to -1.12 into our equation 3, we get amplitude times sine of -1.12. And since amplitude is a positive quantity, the sine of -1.12 is negative, so this result would be negative. We can also check with equation 4. We substitute phi naught equals to -1.12. We get angular frequency times amplitude times cosine of -1.12. And we get a positive value. How about solution B? If we substitute this phi naught into equation 3, we get amplitude times sine of 2.02. And we get a positive result. In equation 4, we get angular frequency times amplitude times cosine of 2.02. And we get a negative initial velocity. But what are the initial conditions given in the problem? Initial conditions for displacement is positive 2 centimeters, which is positive. So solution A gave us the wrong initial displacement, and solution B is the correct one. Then it should be consistent with velocity. Let's see that. It's given that initial velocity is negative 2. Solution A gave us the wrong sign. Solution B gave us the correct sign, which means the phi naught for this wave is 2.02 radians. And lastly, to complete the displacement function, we need the amplitude. To find the amplitude, we can substitute our phi naught into either equation 3 or equation 4. I'm going to use equation 3, but you'll find the same result if you substitute phi naught and angular frequency into equation 4. So let's sub phi naught, which is 2.02, into equation 3. And we get amplitude times sine of 2.02 equals to 0.02 meters. Then we solve for the amplitude. And we get 0.022 meters. So we found the 4 quantities we need to write down the displacement function. We found the wave number equals to 8.38. And angular frequency is 209.4. We also found the phase constant is 2.02. And amplitude is 0.022. So, let's go back to our equation 1 and equation 2. Equation 1 is the displacement function. It's a function of x and t. It is amplitude times sine of wave number times x plus, it's a plus sign here because it is a left traveling wave, plus angular frequency times time plus the phase constant. So we substitute the quantities we found. The displacement function is 0.022 times sine of wave number times x plus the angular frequency 209.4 times time plus the phase constant 2.02, and unit is meters. In equation 2, it is the transverse velocity function, which is angular frequency times amplitude times cosine of wave number times x plus angular frequency times time plus phase constant. We substitute the numbers we found. Angular frequency times amplitude is 4.61, then cosine of 8.38, the wave number, times x, plus angular frequency 209.4 times time, plus the phase constant 2.02, and unit is meter per second. And that is the end of the video. If you have any questions, feel free to comment below. And if you like my videos, please like and subscribe, and I'll see you in the next video.